Okay, in section 1.7, we're going to be looking at the idea of linear independence. Okay, and again, a lot of these concepts in chapter 1 relate to each other, so we're going to rely heavily on the things that we did in 1.5, for example, when we were talking about solution sets, and in 1.4, we're talking about linear combinations. All of that plays a role here. So when we're talking about linear independence, we shift the focus just a little bit. We've been talking about the matrix equation, AX equals 0. Remember, 0 is a vector and X is a vector, where A is a matrix. And to this point, we've been talking a lot about this vector X, right? We've been looking for these solutions, say if it was a three-dimensional or a vector in R3, we've been looking for those X1s, X2, X3 to represent that, okay? Well, when we're talking about linear independence in 1.7, we shift the focus a little bit, and we're going to talk about the matrix A more instead of looking only at the vector, the solution vector, right? So we're going to be looking here instead of looking here, okay? So we're looking more at the matrix when we're looking at linear independence, okay? So let's start with a vector equation, similar to ones we've seen. Let's just write one down here. So I've got x1 times 2, 1, negative 1. We're going to add that to an x2, which is times another vector, negative 1, 0, and 2. And then times x3, which is a third vector, 3, 1, 1. Okay, and we're going to make this a homogeneous system, so we're going to set that equal to the 0 vector, 0, 0, 0. Okay? And what we've done to this point is we have solved this system, right? So maybe I set up a matrix, 2, 1, negative 1, using my column vectors as my columns of my matrix. I augment that with zeros, okay? And I do some row operations, or perhaps I compute it using my calculator, right? It's going to be a 3 by 4 matrix. Type in your points along your matrix, type in those values, and then do the reduced row echelon form. And what we get out is a nice, pretty diagonal matrix, again with zeros in that far column. So this system has only the trivial solution, right? The only solution is x1, x2, and x3 are all 0. That's the only solution. There's no other solutions, okay? So we're going to tie this idea into linear independence, okay? So vectors are said to be linearly independent. So vectors are linearly independent. So vectors are linearly independent if x1 v1 plus x2 v2, you should recognize our vector equation, all the way out to some xn vn equals 0. So that's our standard vector equation for a homogeneous system, has only the trivial solution. Okay, so they are linearly independent if you have only the trivial solution. So what that means is my vectors that I had in my previous example, this 2, 1, negative 1, negative 1, 0, 2, and 3, 1, 1, are said to be linearly independent. Okay? Now, naturally, we're going to have a corresponding definition for linearly dependent. Okay? And much as with many previous definitions, we tend to shorten that verbally to just independent or dependent. A lot of times we leave off that word linearly because we're in linear algebra. We know we're talking about linear equations and linear systems. Okay, so those vectors are dependent if our vector equation, x1, v1, x2, v2, as many vectors as we need, all the way to xn, vn equals 0, has a non-trivial solution. Okay, and now I've said a non-trivial solution, but in reality, if you have one non-trivial solution, as we saw in section 1.5, if you have one non-trivial solution, you really have infinitely many non-trivial solutions. Because if you have a non-trivial solution, remember that means the same thing as having a free variable. And if you have a free variable, that free variable could be 1, 2, 85, pi, you can put anything in for that free variable, and that free variable will determine what your basic variables are. Remember the opposite of a free variable. is a basic variable, okay? Now, this equation here that has a non-trivial solution is called the dependence relation, right? So if I have this equation, right, remember non-trivial solution means that there is some x sub I that is not 0 along the way. So they can't all be 0, that's the trivial solution. Okay, and so one of these where some x sub I is not 0 is called the dependence relation. Okay, so the dependence relation is where I have x1 v1 plus x2 v2 xn vn equals 0 with xi not equal 0 for some index I. Okay, so you just need one such thing to accomplish the task. Now, once you have one, you really get infinitely many more, but once you locate one, you have them all. Okay, and so we've seen some examples with that when we were talking about linear combinations. Okay, we looked at some of that. And so let's, for the sake of an example, let's say that x1 v1 is my one that's not 0. So let's just write a simple one, x2 v2, and then let's stop at x3 v3. And that's equal 0. Well, if I say that x1 v1 is, if I say x1 is not 0, I can take that x1 to the other side. So x2 v2 plus x3 v3 is equal to negative x1 v1. Okay, so this vector then now is a linear combination. Remember, this is exactly the definition of a linear combination. If I have a vector on the right, that I can take multiples of the vectors on the left, sometimes just one vector, right? We did that with multiples of vectors. We talked about how the span gave us a linear appearance. Right? But if I can take any combination of these vectors and get another one, that dependence relation gives me the linear combination. It also shows me that this set of vectors, v1, v2, and v3, are linearly dependent, okay? And so this relationship is the dependence relation, okay? Now, we've talked about it in terms of vectors. We've also talked about it in terms of matrices. So we can use vectors or matrix columns interchangeably. Okay, it applies to both. Okay, so if I take my vectors from earlier, right, I had the vectors 2, 1, -1. My next vector was -1, 0, 2, and my third vector was 3, 1, 1. Okay, so these vectors are linearly independent based on what we did in the system, or I could have written it as a matrix originally instead of as a set of vectors. And if I write that as a matrix, then we would say the columns of A are linearly independent. So these are either independent vectors, sorry, can't spell today, either independent vectors or independent columns. And as we've seen throughout chapter 1 so far, we can use the vector notation and the matrix notation interchangeably and talk about basically all of the same things. Okay, so let's further this with some more examples on linear independence. Okay, so for our next example, we're going to look at, we've got 5, 0, 0, 7, 2, -6. And then my third vector is going to be -2, -2, and +6. Okay. And so we're asking, are these vectors independent? Are they dependent? If they are independent or dependent, what would the dependence relation be? Right. So again, I'm going to take my matrix here, 5, 0, 0, 7, 2, -6, -2, -2, and 6. And I told you in the last couple videos that I would likely stop augmenting that column of zeros. Okay, so it's really not a necessary thing, but know that that is what we are looking at, is with that augmented. We know we're looking at the equation ax equals 0. Okay, so we can imagine then that I have that row of, that column of zeros, I should say, augmented. But when we do row operations or REF, with a column of zeros, we know we're just going to get a bunch of zeros in that column. So we don't have to write that column down every time. Again, go to your calculator. Okay, again, second matrix, right? It's above X inverse. Okay, got a little ahead of myself there. Second matrix, go over to edit. Okay, you can edit any of your matrices. I usually do most of my work in matrix A just because it's easy to do that. The first one, I've got a 3 by 3, so type 3 by 3 there. 5, 7, -2, 0, 2, -2, 0, -6, and 6. Okay, so quit and then do RREF. And so I get that matrix when I reduce it, 1, 0, and then 1, -1 in the third column. Okay, so I've got 1, 0, 1, 0, 1, -1, and then all zeros along the bottom. That's a positive 1 there in that first spot. It's a -1 in the second spot. Okay, so we can see here that x3 is free. It's a free variable. Okay, so I do have a free variable. So that means that the system or the vectors or the columns of matrix A are dependent, right? So we can either talk about these three vectors being dependent or these three columns of the matrix being dependent, talking about the same thing. We can do the same operations to find out, okay? So x3 is a free variable, okay? I could write a solution set just for practice, so we'll do it here. So I move that free variable over to the other side of the equation, because remember it's equal 0, so I get x1 is equal to -x3. x2 is also equal to positive x3, and then x3 is our free variable, so it's x3. I could write that in vector form, right? Vector form would be -1, 1, 1. Okay, it's lots of choices there. I can also write the dependence relationship here. Okay, so let's look at what we have, right? What's getting added to make this? So I have -1, -1, 1, okay? So if I take a copy of x1 and I subtract x2, that gets me x3. Not x, sorry, I said x, that should be v. Those are the vectors, right? We're looking at the vectors, my apologies. All right, so if I've got vector 1, I subtract vector 2, that gets me vector 3. Okay. So let's look at what where those numbers came from, right? This was 1 v1 and -v2. A 1 and -1 gets me this dependence relation. If I go back to my original columns, I have 5 minus 7 is -2. 0 minus 2 is -2. And 0 minus a -6 winds up being 0 plus 6 gets me a positive 6. So v1 minus v2 is equal to v3. So that would be my dependence relationship here, okay? So there's my dependence relation. Okay, now we have some easier systems, easier sets of vectors to deal with. Okay, we get some kind of simple ones to work with. Let's say I have the 0 vector as one of my vectors. So let's put the 0 vector here with another vector, 2, 1, -1, and a third vector, 3, -1, 0. Okay, well, we're going to label these v1, v2, and v3. And if I think about doing c1 or x1, let's say x1, v1, x2, v2, x3, v3, and I set that equals 0. Well, we know because v1 is the 0 vector, I could actually do anything times v1 and still get 0. And then I can make my other two vectors 0, and that will give me all zeros across there. So anytime the 0 vector appears, the 0 vector is dependent. Okay, because anything times 0 will still be 0. So if you have a system containing the 0 vector, you know that's going to create a dependent system. Okay, or a dependent set of vectors. Okay, so any appearance of the 0 vector makes your set of vectors dependent. Okay, now another property is I just have a single vector. So let's make our vector whatever we like, 2, -1, 3. Nice vector. Is that vector independent? Well, if I do x1, v1, because I only have the v1, and I set that equals 0, the only thing x1 can be is 0. okay? So any single vector, I don't have anything to offset it or to fix it with, to cancel it out, right? If I just have the one vector, any single vector has only the trivial solution and thus is independent or linearly independent, okay? This equation has only the trivial solution, so the vector has to be independent. Now, you do have to think about these two ideas that I just posed here in concert. You have to think about them together. If my single vector is just the zero vector, well, that's actually dependent. So we need a sort of parenthetical, unless you have the zero vector. Okay, so think of it as rule number one, the zero vector is dependent. Okay, if you don't have the zero vector, then any single vector is independent or linearly independent. Okay, but if you have just the zero vector, it's dependent. That was sort of step one. You don't even get to step two. So the zero vector is dependent, but any single vector other than that zero vector is independent. Okay. Now, the nicest sets of vectors for us to deal with are when we just have two vectors. So let's take two vectors here. We'll just make these in R2 this time, 2, 1, and 4, 2. Call them V1 and V2. Well, I can already see that V2 is double V1. So I know there's a relationship where V1, 2 times V1 is equal to V2. Hey, that relationship should be evident. And so this is a dependence relation, right? I have my two vectors set equal to each other. If I subtracted V2 to the other side, I would get it to look like a homogeneous system. Okay? So that is a dependent system. So if you have two vectors and they're multiples of each other, that gives you a dependence relation. That actually tells you the dependence relation, and that tells you that those vectors are dependent. Okay? Now, we can make them bigger vectors, 1, 0, 2, -1. Say they make vectors in R4 now. And we'll do 3, 0, 6, -3. Okay, well, I can see quickly that V2, my second vector here, is 3 times vector 1. So 3V1 is equal to V2, or if I wanted to write it as a homogeneous system, I'd have 3V1 minus V2 is equal 0. And so this is a non-trivial solution. Okay, I could set up a matrix, okay, just showing you how all these different pieces interact. Okay, I could set up a matrix here, 3, 0, 6, 3. Okay, so I've got the columns of my matrix. I could row reduce this matrix. I would get 1 and I would get all zeros down below. Okay, don't forget the negative sign here. All right, make sure we get that vector written down correctly. And so then I'm going to get 1, 3 because I know that this is 3 times vector 1. Okay, so if you set up a solution set based on this information, right, I would have x1 is equal to -3 x2. X2 would be our free variable. Okay, so most often, right, we would pick x1 to be 1. Or x2, I'm sorry, my free variable. If I pick x2 to be 1, then I get x1 would be -3. And so you see there's also a dependence relation here that would have -3v1 plus v2 is equal to 0. That also gets me that dependence relationship. So there are multiple dependence relationships, okay? Whether you have positive or negative, negative or positive, okay? Because remember, we're working off the standard vector equation, x1 v1 plus x2 v2 is equal 0. Okay, and if we find a non-trivial solution to that, then we know we have a dependent system or a dependent set of vectors. Okay, so when you're dealing with just two vectors, You only need them to be not either multiples of each other or not multiples of each other. All right, so it doesn't matter how big the vectors are. I'll take two vectors here in R5. Okay, as I look at these two vectors, V1 and V2, clearly there is nothing I can multiply V1 by to get V2. So V1 is not a multiple of V2. Okay, and when that's the case, you have independence. You have independent vectors or linearly independent vectors. Okay, or linearly independent columns if you wrote it as a matrix. So two vectors is the nicest case. Well, one vector is the nicest case. Two vectors is next nicest. And remember, anytime you have a set with the zero vector in it, you can immediately figure that set is going to be dependent. Okay, it's got the zero vector in it, so dependent has the zero vector. Okay, so zero vector makes things easy as well. Now, if you have more than two vectors, so let's look at a set here, 2, 1, -1. Make our next one 4, 2, -2. And then the third vector is 1, 1, 1. Okay, so as I look at these vectors here, I can see then that V1 and V2 are multiples of each other. Right? If I multiply V1 by 2, I get V2. I can see that 2V1 is equal to V2. Okay? So that means I could set up a dependence relation, 2V1 minus V2, and then it doesn't matter what happens to V3. Actually, it does matter. I need to make it 0 because it doesn't line up here. But remember, it's okay for some of your weights, some of your linear weights or your coefficients or your x's. It's okay for some of those to be 0. It's okay for this one to be 0. They just can't all be 0. Okay, so these vectors are dependent because I have two vectors that are multiples of each other. Okay, now we could also, if you didn't recognize that they were multiples of each other, you could just set up your matrix and then use your calculator to row reduce that matrix. So I've got 2, 4, 1 along the top, 1, 2, 1 in the middle, -1, -2, 1 along the bottom. When I row reduce that, I get 1, 2, 0, 0, 0, 1, and then all zeros along the bottom row. Okay, and so as I look at this, I have a pivot here and a pivot here. Okay, now remember that it's like this is augmented with 0 because we're looking at the dependence relationship, okay? But I didn't write down that augmented column of zeros, okay? So I see that x2 is a free variable, but x1 and x3 are not free variables. So if I just take the two vectors, v1 and v3, v1 and v3 are independent. Okay, v1 and v3 are independent. V1, V2, and V3 together are dependent. Okay? So we also have to think geometrically. So geometric and the span and all this fits together, right? If I have two vectors that are independent, that would give me a plane. In this case, it would be a plane in R3. And that would be a plane in R3. Even these three vectors that are dependent, remember this second vector v2 is just in the same line that v1 is. So these three vectors together also make a plane in R3. Okay? Now we have a few more possibilities of things that can happen. I can have too many vectors. When I say too many, I'm using that kind of loosely, but you'll see what I mean as I talk about the property here. So I have these four vectors that are all in R2. Okay? Well, if I think about writing these as a matrix, 1, -1, 3, -1 across, 2, 1, 2, 1, -1. Notice that none of these vectors are multiples of each other, right? I can't well, I said that. Let me fix that. Now none of these vectors are multiples of each other. That's what I want. Now none of these vectors are multiples of each other. Okay, I can't multiply one and get another one. But if I look at my matrix, the most pivots I can have is 2. Remember, you can only have a pivot in each row. You can only have one pivot per row. So with just 2 pivots, I don't have enough rows to get these to be independent, right? You know, it doesn't matter where my 2 pivots are. If they're here and here, maybe they're first and third columns, I'm going to have 2 free variables. Okay? So if there are more vectors, than entries in the vectors, the system or the set is dependent. You must have a dependence relation, I should say, not ratio, if you have too many vectors. Okay, now that only works in one direction. Okay, because if I have more entries than there are vectors, that's not a guarantee. Okay, remember we had an example up at the top of the page here. This has 5 entries, but only 2 vectors. But those vectors are still independent. Okay? Okay, so that's a property that only goes one way. If there's more vectors than entries, it's dependent. But if there's more entries than vectors, that doesn't tell you anything. Because you can still have 2 vectors that are multiples of each other. You can still have 2 vectors that are not multiples, and thus they would be independent. Okay? Now, I have a couple more problems, in particular some kind of types of problems that you might see in the homework. So first, let me get this nice and visible here for you. So first, we're going to have 3, -3, and 6. Second vector is going to be 6, -9, and 11. And then my third vector is going to be -2, 2, and h. And the question is going to ask us what values of h make an independent set or a dependent set. Okay, so you have to pay attention to which thing the question is asking for. Is it asking for it to be independent? Is it asking for it to be dependent? So I'm going to work on both with this system just so we're prepared. But you have to make sure you see what that question asks. So 3, -3, 6. I'm going to make a matrix. 6, -9, 11. -2, 2, and h. Okay. Now we're going to start row reducing this. Okay, so I'm going to do row 1 plus row 2 and replace row 2, right? I can't just use my calculator because I got this h running around, kind of ruining things for us. Okay, so row 1 plus row 2, because that's going to give us 3 and -3, okay, which will make 0. I can also do -2 row 1 and add that to row 3 and replace row 3, because -2 times 3 will give me -6, and 6 and -6 will give me 0. So row 1's not going to change, 3, 6, -2. Row 2 now, 3 plus -3 is 0. 6 minus 9 is a -3. -2 and 2 is 0. Okay, row 3 now, -6 and 6 makes 0. This is going to be -12, and 11 is going to make a -1. Then we're going to go here, we've got +4. -2 times -2 is a +4, and we're adding that to h. So I have 4 plus h for that third one. Okay, so remember, you go down the first column, then we go over to the next one and go down. Okay, so on the second one here, I'm going to quickly scale this. I can see that this can be easily scaled to be taken care of. I'm going to go ahead and multiply the first row by, or divide the first row, I should say, by 3, so that I get just ones there. I'll get a fraction here, but I'll only have ones there. So we're going to take row 1, divide it by 3 and replace row 1. We're going to take row 2 and divide it by -3 and replace row 2. Okay, so my new matrix now is going to be 1, 2. I divide that, so I get -2/3 for the last spot there. 0, that's going to be a +1 now, and 0, because 0 divided by anything is still 0. And then row 3 did not change, so it's still 4 and -1 and 4 plus h. Okay, that makes this replacement operation pretty easy. I can do row 2 plus row 3 replaces row 3. Okay, so I've got 1, 2, -2/3. Then I have 0, 1, 0, no changes there. And then the last one's going to be 0, 0, and 4 plus h. Okay? All right, so now if we think about this in terms of a dependence relationship, I have a pivot here and a pivot here, and I have a possible pivot here, okay? So if this is a pivot, then I have independent vectors because I have a pivot in every row. A pivot in every column, I should say, sorry. I have no free variables, right? If it's a pivot, I have no free variables. So a pivot's going to be no free variables. Now, the only way this wouldn't be a pivot is if I get 0. So that's if it does not equal 0. It's not a pivot if it equals 0. Okay, and if that's the case, then I have x3 is free. Okay, so remember then, no free variables is independent, and a free variable is going to mean that it is dependent. Okay, so when is it 0? Well, when 4 plus h is 0. So 4 plus h equals 0 means that h is equal to -4. Okay, so if h is -4, it's not a pivot. Draw a line here to emphasize this, right? H is -4, not a pivot. Does it equal 0? Means that's a free variable, means it's dependent. Well, if I do 4 plus h not equal 0, that means h does not equal -4. Okay, so all the possible real values of h are covered. It's just that one of them makes it dependent and any of the others make it independent. Okay, so you're trying to figure out if you can get a pivot for every column. If you've got a pivot for every column, you have an independent set. What would cause you not to have a pivot? Well, if you have all zeros. If you have all zeros, you have a free variable. And if you have a free variable, then you know what your situation is. Okay, we don't have to worry about going up from there. Okay, because if this is a pivot, then I could do the row operation to put that together. Okay, but we don't need to know what that row operation is. It didn't ask us for that setup here. It just says, is it independent? Is it dependent? Okay. Another thing that you might be asked is, how many pivots do you need? So let's say I have an 8 by 6 matrix. Okay, 8 by 6 matrix. How many pivots are needed for the columns to be linearly independent? Okay, so let's think about what an 8 by 6 matrix looks like, right? Remember, it's rows by columns, okay? So I have 8 rows and 6 columns, okay? So if the columns are going to be linearly independent, so I'm going to make these bubbles here to represent my columns. So I got 6 bubbles there for 6 columns. If the columns are going to be independent, I need a pivot. I'll put a P for each one. So the number of pivots I need is equal to the number of columns. So how many pivots do I need? I need 6 pivots to be linearly independent. If I have fewer than 6 pivots, then one of them is dependent. Not one of them. The whole set is dependent. Okay, the reason I said one of them is I'm thinking ahead to the next thing. However, if I have one of these that's not doesn't have a pivot, okay, so let's say that fourth one there does not have a pivot. Well, now if I get rid of this vector, so let's name our vectors v1, v2, v3, v4, v5, and v6. Okay, so now the set that contains all of them is dependent. But I can toss aside the one that has that situation that makes that free variable. So if I toss aside that fourth vector and make a new set that's just v1, v2, v3, v5, and v6, that new set is going to be independent. Okay, so you can identify just the ones that have the pivot columns, and that will tell you which vectors make an independent set. Okay, if you have a vector in there that doesn't make a pivot column, then that's going to be a dependent set. It makes the whole set dependent, but we can take some out to make an independent set. Okay, so to give you a quick example of that idea with some concrete numbers, if I have 1, 1, 1, 3, 3, 3, and negative 1, 0, 1, clearly I can see that these two vectors, these first two, are multiples of each other. Okay, so these first two vectors are multiples of each other, so that means the whole set here, which I'll call v1, v2, v3, is dependent. But if I throw away this v2 vector that is not in the set, or that doesn't add anything new because it's just a multiple of v1, v1 and v3 together are independent. Okay, if you row reduce this, you would get a pivot in the first column and a pivot in the third column. Okay, which would tell you that those two vectors are independent, but the v2 vector is what is throwing things off. It's what's messing things up. It's keeping you from having an independent set. Okay, now since I only have two vectors, this would be a plane in R3. So remember, if you have two vectors, it's a plane. One vector is a line. Three vectors is a hyperplane. Okay, if you have as many vectors, so right now I have three vectors and three variables. Okay, so that's good, but one of them didn't line up. Okay, but if I have another set, so let's say 1, 1, 1, make this one negative 1, 1, 1, and my third one would be negative 1, 0, 1. These three vectors are independent, so these three vectors actually generate all of R3, which is a hyperplane, but it's all of R3 because I have as many vectors as I do entries in my vectors. Okay. I also remember, I touched on it earlier. If you have one relation, you have infinitely many relations. Okay. So I want to jump back to that because I know that's a question on the homework has something similar to that. You see, if I can set up one dependence relation, I can actually make any number of dependence relations, right? I could multiply these both by 2. I could get negative 6, positive 2 here. That would give me another dependence relation. So you can create lots of dependence relations just from one set of vectors. Okay. All right. So that should finish our discussion of linear independence. Okay. Again, if you have questions, please be in touch with me. I'm happy to help. Take a look at those homework problems in my math lab. Should be at this point getting ready for some of the first checks for understanding, those true-false quizzes for the quizzes as well. Starting to get to those sections where you've done all the material for those sections. So make sure you go through those processes and make sure you're staying up to date on all the due dates. Okay. Please be in touch if you have questions, and I'll see you next time for section 1.8, where we start talking about linear transformations.